Welcome to Ushendra's engineering tutorials. Z transforms plays a very major role in signal processing, more precisely digital signal processing. It plays a very key role in digital signal processing. Z transforms, and we have many properties of Z transforms. One of the important property being time shifting property, which is the starting point for many discussions in digital signal processing. What is Z transform actually? So the discrete signal x of n will be given. Okay, x of n will be given. It may be y of n, it may be something else of n. So obtaining the Z transform, this one, and its notation x of z transform will be equal to what? How to evaluate the Z transform of any given function? The given function x of n is multiplied with z raised to minus n and summation from n equal to minus infinity to plus infinity for a both-sided Z transform, to obtain the both-sided Z transform. And on the other hand, for a causal signal we have summation, it's n equal to 0 to positive infinity x of n z raised to minus n for a causal which exists for n greater than or equal to 0, right? So in this case, if this is the case, what will be the Z transform of x of n minus n plus m something, n minus m? No, straight away a value for the beginner to understand. You don't have much time, right? So what will be the Z transform? This one will be equal to the same. The given signal x of n plus 2, isn't it, is multiplied with what? This given signal. This is the given signal, and in order to evaluate the Z transform, this one, the given signal is multiplied with z raised to minus n, and the summation is from n equal to minus infinity to plus infinity. We'll make use of that also when time comes. For the time being, this is the way, this is a procedure to evaluate the Z transform of the given function. Bilateral, both-sided Z transform extending from minus infinity to plus infinity, right? So we need to go for some substitution over here. Inside the bracket we need to go for some substitution. Let's say let's substitute that with n plus 2 equal to some p. Okay, so in that case we need to have the value of n. With this substitution, making use of this substitution, we need to what will be n, because we need to plug in n will be equal to p minus 2, isn't it? Here p minus 2 in this case. And in maths, while we do maths, like when we go for substitution, with n equal to p, this one, it's a constant, and there will be a change in the limits also, limits of summation. And how to evaluate this very equation help us to find out that when n starting from n equal to minus infinity, here n equal to minus infinity over here, n equal to minus infinity plus 2, p will be, because p will be infinite, anything it will be lead us to infinite, minus infinite, right? So that's for the lower limit. And when n equal to positive infinity, plugging in the same value over here, p is equal to plus 2 plus infinity, infinite plus any value, that will be infinite, right? So when we have this conclusion, when n starts from minus infinity, p also starts from minus infinity. When n starts from positive infinity, p also will start from positive infinity, right? So making use of this information, we can plug in over here. So what is that? Even this will be x of z, don't worry, the notation, right? So Z transform of x of n plus 2, right, will be equal to what? Summation, after the substitution, it's no more n, it will be p, which is equal to minus infinity. It starts the same. When n starts from minus infinity, p also starts from minus infinity, and the same limits with a positive. And x of, yeah guys, here n plus n we assume to be p, right? So p and z raised to minus n. Here this n, we have that negative over there, n can be plugged in with p minus 2 here, of p minus 2. Okay, so going ahead, it's a summation p equal to minus infinity to plus infinity x of p, and this could be written as minus p into z raised to negative into negative, that will be positive. Okay, plus 2. It's 2, it's not z. Okay, it was similar to, it's a 2. So this is the case. And if this is, guys, summation in the expression, summation is for p. Wherever we have p, that will be inside the summation, and other than those terms without p, that can be taken out, treated as a constant, and that can be taken out. This z raised to minus 2 has got nothing to do in the summation, so that can be taken out. This z raised to positive 2 into summation p equal to minus infinity to plus infinity, x of p here, and z raised to minus p. Okay, that's why. Can you see? It's similar to n equal to minus infinity to infinity, x of n, z raised to minus n. When p equal to n, it will be z raised to 2 as it is, summation, here it will go back, like n equal to minus infinity to positive infinity, x of n, z raised to minus n. Now what is this entire thing? What is this summation? Guys, what is this summation? It's z raised to 2 x of z, isn't it? So this is the shifting property, the final shifting property of a z transform. So what will be in that case? What will be the z transform of x of n minus 2 here? That will be z raised to minus 2 x of z. Keep this in mind. We will, like, it has got a lot of application in digital signal processing. Make a note, please. So one of the important application of that property which we have seen right now, the shifting property, obtaining the, it will be asked to obtain the direct form one, a physical realization of digital filters. So what will be the z transform of this entire equation? Any equation will be given, and it will be asked to obtain the direct form one of that given difference equation. This is the one. So what will be, just now we have seen that time shifting property. According to that, what will be the z transform of this one? This will be simply y of z. Z transform of x of n will be x of z. Z transform of y of n will be y of z. A uppercase letters, okay, which is equal to, it's a constant, minus 13 by 12 as it is. And here comes our shifting property. If this is the case, it will be z raised to minus 1 y of z. Minus of this is a constant, 9 by 12. Here, making use of the shifting property again, z raised to minus 2 y of z. This is the case, and we are done with this. Okay, so this one minus 1 by 2. This is z raised to minus 3 y of z, according to shifting property again, and plus x of n, it will be x of z, plus this will be 4 times z raised to minus 1 x of z, isn't it? Previously it was, yeah, this one, plus 3 times z raised to minus 2 x of z, y of z and x of z in uppercase, the notation, right? So in this case we need to have a physical structure of this one, and it's a well-known thing that y of z is the output and x of z is the input over here. We'll be having, guys, we'll be having x of z over here, x of z, and y of z somewhere else here. Let's say y of z is somewhere else here. So how to represent this part here, from here to, that will be easy for a beginner to understand. And this one, z raised to minus 1, z raised to minus 2, are known as delays while in designing a digital filter, obtaining the realization of the digital filter. Z raised to minus 1, z raised to minus 2, these are known as delays. Okay, so it's straight away plus x of z. In the sense, we have this one, we have a summer over here, we have a signal, like straight away it's plus, and it's x of z comes over here. Okay, so we are done with this one. We are done with this. How to show this one? It's a positive 4 times x of z, z raised to minus 1. We have here, we have x of z over here, multiplying with a delay element. It's a, here, the delay element being z raised to minus 1 over here. It's multiplied, x of z, z raised to minus 1, and still a multiplier over here with what value is that? it's a 4, positive 4, okay, and a summer over here with a positive, and that goes, it's a positive over here, okay. So that gives this one. And how to construct that one? Another delay element, guys, another delay element, same, z raised to, it's not z raised to minus 2, it's z raised to minus 1. Why? Because x of z into this one, x of z minus 1 into this one, z raised to minus 2, that will give us. So a signal flowing in this direction, that will give us, up to this point, it's z raised to minus 2. Here we have z raised to minus 2 into x of z, and some another multiplier over here. What amount? It's a positive 3. So this is the case. Added and added and add again. Okay, so we are done with this part. So come back, we need to construct this one also. So we already have here, we already have this one. Let's go for a sum over here. We already have y of z, okay, y of z is here. So how to show this one? It's a, if we connect a wire over here, the same y of z will be flowing over here, isn't it? So we have y of z into z raised to minus 1, so a delay element with z raised to minus 1, and this should be multiplied, isn't it? This should be multiplied with what? It's we need to have a multiplier over here, with what value is that? Minus of 13 by 12, okay. So a summer over here with a positive, and signal goes and gets added over there, right? So we are done with this one. This is how this one is done. Now how to show this one? It's a negative of this one. Again, it's z raised to minus 2, so we need to have another delay element over here. Here it's another delay element, same z raised to minus 1, and this, at this point, we'll be having y of z into z raised to minus 1 into z raised to minus 1, that will be y of z into z raised to minus 2. So y of z into z raised to minus 2 we have. So going for a multiplier over here with like this structure, it's a multiplier, the notation of a multiplier with what? Minus of 9 by 12, okay. So with a summer over here with a positive, the signal goes and gets added over here, nice, right? Because we have a negative over here, so that gets added over here. And how about this one? The same procedure. We have y of z. Up to this point, it's y of z into z raised to minus 2, having another delay element over here. It's another z raised to minus 1 over here, z raised to minus 1. So now we here, after this, we'll be having like y of z, z raised to minus 3, in the sense y of z, z raised to minus 3, and another multiplier over here, it's with a minus 1 by 2, and no need of summer because this is the last element, okay. So this gets added, in the sense the entire thing is added with this one, which is our final y of z, okay. This is our final y of z. Look carefully, how many, what is the order of the system? I mean, what is the order of the differential equation governing the system? It's a 3, isn't it? So it's a the order is 3, but how many delay elements we have? It's a 1, 2. Like finally, what I want to conclude is, in this direct form 1, the number of delay elements which is used to construct is larger than the order of the system, and so this is known as a non-canonical form of realization. Non-canonical form of realization. Direct form 1 is also known as non-canonical form of realization. Make a note, please. Direct form. This is the Z transform of this entire equation, and that procedure to obtain the direct form 2. Let's see how to evaluate the direct form 2. Here we need to arrange the entire equation in a transfer function, y of z by x of z. That will be here y of z, and it's a negative, even this is negative, that pulling this side, that will be all positive, and straight taking away y of z of, guys, this side it's a negative, coming this side it will be positive, even this is negative, coming that side it's positive, even this is negative, coming that side it's positive. And one more thing, y of z from here, 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 and here. So taking out that as common, y of z as taking out y of z as common from this one, we have 1, and from here plus it's a, yeah, it will be positive, right? It will be 13 by 12 z raised to minus 1, and even this will be positive, plus 9 by 12 z raised to minus 2, taking out y of z as common, plus 1 upon 24 z raised to minus 3, y of z came out, so this is the one, which is equal to, taking out, it's here, okay, all these are shifted to LHS. Now taking out x of z as common from this one, entire equation here, over here, from this side, we are left with 1 comes from here, and 4 raised to z minus 1 from here, plus 3 raised to z raised to 3 into z raised to minus 2 from that one. So what will be the transfer function? Output by input, isn't it? So y of z by x of z will be equal to what? So this comes this side and flipped up. This gets flipped. 1 plus 4 raised to 4 into z raised to minus 1 plus 3 into z raised to minus 2 upon, this gets flipped, right? 1 plus here 13 upon 12 z raised to minus 1 plus 9 by 12 z raised to minus 2 plus 1 upon 24 z raised to minus 3. Guys, this one. Now a small change, something adding, introducing something. What is this? It's a y of z by x of z, isn't it? So what if we do some another element comes in between? Let it be multiplying with w of z in the numerator and in the denominator as well. Okay, so here this one, this very expression y of z of x of z, and a small change over here, a small rearrangement over here. What if we have w of z by x of z here into these two, and y of z by w of z. Okay, so this is the change. In the sense, how can this be written as? It's a 1 by 1 plus 13 by 12 z raised to minus 1 plus 9 by 12 z raised to minus 2 plus 1 by 24 z raised to minus 3, isn't it? This entire into, can this be written as this one? Into this one, 1 plus 4 z raised to minus 1 plus 3 z raised to minus 2 by 1. So multiplying this, we'll get back to that. So now considering this ratio, now this one, let us consider this one. It's a w of z by x of z, let this be this ratio, into, it's into, right, into, and y of z by w of z, this ratio. Now what is the expression for wz of x of z? We have wz upon x of z, which is equal to 1 upon here 1 plus 13 by 12 z raised to minus 1 plus 9 by 12 z raised to minus 2 plus 1 upon 24 z raised to minus 3, isn't it? On the other hand, we have y of z by w of z is equal to 1 plus 4 into z raised to minus 1 plus 3 times z raised to minus 2 from this very simplification. Now cross multiplying this one, what we have is a w of z into straight away multiplying, okay, 1, so w of z plus 13 by 12 z raised to minus 1 into w of z, this one multiplying, plus 9 by 12 z raised to minus 2 plus, into w of z plus 1 by 24 z raised to minus 3 w of z, which is equal to x of z, isn't it? X of z. Now what will be, which is equal to x of z from here, cross multiplying this one. So what will be our w, simply w of z from here, which is equal to x of z minus this one, it's a positive, to RHS that becomes minus 13 by 12 z raised to minus 1 w of z plus, even this is minus 9 by 12 z raised to minus 2 w of z minus 1 upon 24 z raised to minus 3 w of z. We're done with this one. So this is for w of z. Okay, so coming to this side, what we have, y of z, from this very expression y of z will be equal to y of output y of z, final output y of z will be equal to, cross multiplying this, it's a w of z plus 4 times z raised to minus 1 w of z plus 3 times z raised to minus 2 w of z. Okay, so this is the expression for y of z. Making use of this one, we can construct the, making these equations, we can construct the direct form too. Let's say like x of z is over here, let's suppose, and w of z over here. From making use of this expression, it's a x of z here, it's a plus x of z. Okay, so straight away we have over here and this one, right? And how to show this one? So how to show this? We already have w of z over here, w of z multiplied with the delay element over here, multiplied with the delay element, that's z raised to minus 1, and a multiplier, what amount of multiplier? Minus 13 by 12, and with the summer over here, it's the procedure plus. Okay, because we have a negative over here. We are done with this one. And how to obtain this one? It's here, minus of 9 by 12 into z raised to minus 2, and here up to this point we have w of z, z raised to minus 1. So another delay element over here multiplied, that will give us another z raised to minus 1 delay element. Now this one, after this point we have z raised to minus 2, w of z into z raised to minus 2 after this one, and multiplying with how much? It's another multiplier over here with a minus 9 by 12, isn't it? So adding this one, we have this signal gets added over here. Okay, so that's for that one. And another, it's left over, it's a minus 1 upon 24. Yeah, it's another delay element which gives us z raised to minus 3 into w of z, multiplying this with another, this one, what amount? Minus 1 upon 24, isn't it? And this signal gets added over here. We are done with this one. Okay, so how to evaluate for this one? Here we have let's say we have y of z over here, and what's our y of z? It's straight away we have a summer over here. Okay, so w of z gets added here, w of z gets added, so positive, and 4 into z inverse of w of z. At this point we have w of z into z raised to minus 1, right? So we have another multiplier over here. What amount of multiplier is that? With a positive 4. And now the signal flowing through this one, w of z, z raised to minus 1 into 4, this is r, this one, right? So this gets added with it's get added here. And what about this one? W of z into z raised to minus 2 into 3, w of z, and after this point it's a w of z into z raised to minus 2, and going for a multiplier, what amount of multiplier? 3 times, and this signal gets added over here, right? This is the direct form to structure of the given equation which you're talking about, right? Can you say this? The number of delay elements over here, the number of delay elements are, hey guys, it's not 3, it's 1 again, z raised to minus 1, don't get confused, right? So number of delays 1, 2, 3, which is equal to the order of the given differential equation. And so this is known as a canonical form. The previous one was non-canonical form, and now this direct form too is known as a canonical form. The reason is the order of the system, the number of delay elements used in constructing the a digital filter is equal to the order of the system, and so. Hope you understood the analysis. Support me with your valuable share and a subscription. Thank you for watching.